Hey everyone, welcome back to Stats class. Um, we are working on 6.1 and I have the PDF posted on Schoology for you. Please have that open so you can kind of follow along. We're going to kind of go back to sort of the way we were taking notes at the beginning of the school year. So kind of following along with the book and kind of taking handwritten notes. So if you have a notebook alongside the PDF, I'll be taking some notes over here, and we'll be looking at the book over here. And yeah, let's hope it goes well. So 6.1, we're going to be talking about discrete random variables, and this is actually a pretty good topic to sort of pick up here on this new format of class, and that's because we actually went over this before. So I kind of got a little bit ahead of myself in the probability unit, and we started talking about things like probability distributions and expected value, that type of stuff. And so 6.1, we're really going to be reviewing some of that stuff again, and then we're going to continue on with more formal definitions of like discrete random variables and types of distributions. Okay, so let's take a look at the book here. So we got our discrete random variables, and if you remember way back to the beginning of the school year, we talked about that difference between discrete and continuous. So let's talk a little bit about that. That's not right. Hold on. There we go. This is going to be 6.1. Let me get rid of that. That's not a very good one. All right, we're off to an awesome start. So 6.1, discrete random variables. Random variables. I hope you guys enjoy my awesome handwriting on this technology here. And so what's the difference between discrete and continuous? So remember way back, we were talking about discrete as things like whole numbers and data that we usually get back from counting. And so that's really one of our main differences. When we talk about discrete, we're usually talking about things that are counted. So data that are counted. And that's an A. It is. And now continuous. Do you remember what we said about continuous data? So continuous data is data that are measured. All right. So that's one of the big differences between continuous and discrete. And so 6.1, we're talking about discrete. In fact, all of chapter 6, so these next couple of sections, we're talking about discrete random variables. Then we'll get into continuous afterward. Okay, so let's take a look at the book. Consider a probability experiment in which we flip a coin 2 times. The outcomes of the experiment are, well, what are all the possibilities? You could get heads, 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 tails, tails, heads, tails, tails. Okay. Rather than being interested in a particular outcome, we might be interested in the number of heads. And so in this case, if we take a coin and we flip it 2 times, what are the possible outcomes if my variable is the number of heads? Well, you could have 0 heads, right? Or you could have had one of the heads, one of those 2 times being heads, or you could have 2 heads, right? So it's either 0, 1, or 2, right? And we're going to be counting that, and so that's why it's a discrete variable. Okay, so here's a definition of a random variable. We've kind of talked about this before. It's a numerical measure of the outcome of a probability experiment. It's determined by chance, and in the book and when I write things, we'll usually use capital letters to represent like the overall variable. Okay, so the capital letter is for the overall variable, and then they use a little x like they have here. So in our coin flipping example, let me bring up there. So like we have right there, the little x is the individual outcomes. Okay, so the capital X is kind of like the broad random variable of how many heads are we going to get. But then that little x, that's the actual values that it couldn't take on. Okay. So anyways, important to remember, discrete random variable counted. Okay, so the outcomes are counted. This is in contradiction to another example right here. Consider an experiment that measures the time between arrivals of cars at a drive-through. The random variable t, so it's a different random variable using a different variable, describes the time between arrivals. So the outcomes that can take on would be anything greater than 0, right? And that would have to be measured. So we couldn't count that, and so that would be a continuous. So that's, again, the sort of difference between discrete and continuous random variables. Okay, and here is a nice little definition again. We've gone over these before, but it's good to refresh our memory when we're restarting something like this again. So a finite or countable number of values. Continuous can take on any value between certain numbers. I really like on the next page this little image they have there. That's a nice explanation, a nice visual of here's discrete, right? It's either 0, 1, 2, 3, or 4. Here's continuous. It can be any number between 0 and 4, right? So, yeah. Example 1, let's just make sure we remember how to distinguish between these things. So let's take a look. The number of A's earned in a section of statistics with 15 students enrolled is a discrete random variable because its value results from counting, right? Okay. The number of cars, usually if it talks about number of something, that's a giveaway that it's discrete because you have to count that. So the number of cars going through McDonald's, yeah, that would be discrete. But the speed of a car traveling by a state trooper, that's going to be continuous because that would have to be measured. Okay, good. Now we're going to talk about the discrete probability distributions. And this is something that we have talked about before. And if you remember, in a probability distribution, it lists all of the outcomes and it lists each individual outcome's probability of happening. So let's take a look at example 2 here. Okay. Suppose we ask a basketball player to shoot free throws. Three free throws. Let the random variable x represent the number of shots made. So x can take on the values 0, 1, 2, or 3, right? If you're going to shoot 3 free throws, you're either going to make 0, or you're going to make 1 of them, or you're going to make 2 of them, or you're probably going to be like me and make all 3, right? Table 1 shows a probability distribution for the random variable x. So here we have our table. So I'm just kind of add this to our notes here. We're talking about a discrete probability distribution now. Discrete probability distribution. Example. So we have our x and our probability of x. And so what values can x take on? Well, we could miss all 3, or we could make 1, or we could make 2, or we could make all 3. And the probability of missing all your shots is 1%, 0.01, right? Because they're called free throws. They're free. Now, 10%, that you make only one of the three, 38% that you make two of the three, and we have a 51% chance that we make all three free throws. Okay, so do you guys remember what we were doing with these probability distributions? First of all, there's two things that have to be true for a distribution to be a valid probability distribution. And so those two things are each probability. Let me start actually with the other one. So because the book has these two rules, which we've gone over, the first one is the sum of all the probabilities must equal 1. And the next one is each individual probability. Each individual probability must be between 0 and 1. Right, because we can't have any negative probabilities, that wouldn't make sense, and we can't have any probabilities that are greater than 100% because that wouldn't make any sense. So yeah, those are the two features we look for when determining whether something's a probability distribution. So hopefully you guys remember those two things, okay? Next, we have an example, right? So which of the following is a discrete probability distribution? So if we take a look at these choices, part A, click over here. So part A, would we say this is a probability distribution? Well, right off the bat, a negative probability doesn't make sense. So that's going to be a no. That's not a probability distribution. Part B, all right, well, I don't see any negatives. I don't see anything greater than 1. So let's make sure it adds up to exactly 1. So if I start adding this up, I got 20%, 25%, I'm at 45, 55, 69% plus 49%. I don't think so. So that's not going to add up to exactly 1. So that is not a probability distribution either. So part C, let's see. Nothing too crazy here. Nothing above 1, nothing less than 0. Add them up. 20, 45, 55, 69%, and then the 100%. So that adds up to exactly 1. So part C would be the probability distribution. Okay. The graphs of discrete probabilities, we're not going to go too much into these graphs, but it is nice to know that we can graph these things. Like, they look a little strange because it's a discrete distribution. So if we can see here, so we got our free throws example, and we just kind of plot the individual outcomes on the X and the probability on the Y. And it's kind of like a point because it's discrete. So there's nothing in between, right? There's nothing happening between 1 and 2. It's just a point at 1, a point at 2, a point at 3. And it's basically just graphing this little table we made in our notes. Okay? So now what we're going to talk about is, let's compute the mean of a discrete random variable. And again, this is something we've talked about. When you calculate the mean of a discrete random variable, all you're doing is you're finding what we called the expected value. So if you remember all that work we did watching the, what was it called? I'm forgetting. Let's Make a Deal, right? So what do we do to find expected value? To find what's called the mean, the average of a discrete random variable. Well, let's jot that down. So Okay, yep, now it's working. All right. The average or mean of a discrete random variable is the expected value. So I'm just going to kind of use that because we've talked about expected value before. So now I'm going to kind of refresh how we find that, right? We multiply each individual outcome by its probability and add all that up. Okay, so for example, in the book, they have an example here. Here is a probability distribution, table 2 here. Let's actually make sure, look at the probabilities. 0.2, 0.1, add them up, 0.3, so we got 0.3, 0.6, 0.8, 1, right? So 100%, so that adds up, and nothing's less than 0, nothing greater than 1. So that's probability distribution. So if we were looking for the outcome, or I'm sorry, the average value of x, we would multiply across, and then we'd add that all up, right? So in this case, 2 times 0.2, 3 times 0.1, 4 times 0.3, 5 times 0.2, 6 times 0.2, and then we add it all up. And so that's kind of what they've done here in the work, in the notes, and we get 4.1. Okay, and so you get an average of 4.1. So if we want to apply that to the example we were talking about before, shooting 3 free throws, and we have this probability distribution, we're going to go ahead and find the average of that distribution. Okay, so let's take a look at, whoops. There's our distribution. Okay. And let me actually rewrite it down here. 0, 1, 2, 3. And we had 0.01, 0.1, 0.38, and 0.51. Right, so if I'm trying to find the average of this, I'm going to multiply across. 0 times 0.01, that's a nice easy multiplication. That's going to be 0. Multiply 1 times that, it's kind of nice as well. 2 times 0.38, what would that come out to be? 0.76, hopefully. And then 3 times 0.51, what's that going to be? 1.53, is that correct? Yeah. All right, so we multiply it across, and then we just add all of these up. Okay, so let's see what we got here. 9, 3, 2. So 2.39. So we get a average of about 2.39 free throws made. So you might be thinking, well, you can't make 0.39 free throws, so should I make my answer 2 or should I make my answer 3? Well, no, actually 2.39 is going to be our answer. So the average, what this means is that if we repeat this experiment, right? So if we continually take sets of 3 free throws, like let's say every day you take 3 free throws every hour of the day, right? That you're repeating that over and over and over again, and you're recording every time how many free throws you made out of the set of 3. If you add up all of those numbers, find the average, the idea is that if you do this more and more times, and if this is your actual probabilities, then the average will be 2.39, right? It'll get there. So that's what we mean by the average of a probability distribution. It's the average in the long run if this trial, if this experiment is done repeatedly over and over again, okay? So there's a good refresher on finding expected value. And the next part of these notes now kind of talks about what I was just talking about, right? So if we continue, bring that cursor back up. If we continue that calculation, if we continue the experiment further and further and further, more and more times, the idea is that we will get closer and closer to the actual probability, okay? And what they did in this book here, they show that they actually did that experiment, right? So here's a bunch of times. They did it 100 times. So 100 different sets of 3 free throws, and they recorded how many free throws they made out of the 3 every single time, right? So here's all that data. If you add it all up and divide by 100, the total number of things you did, find the average, they ended up with 2.35. So 2.35, very close to the 2.39, right? Because as those trials increase, 100 trials, that's a lot of trials. As we increase that further and further, we get closer and closer to that 2.39, closer and closer to the theoretical probability, okay? So, again, expected value. We've kind of covered expected value, so I'm going to skip this little part here. And now what we're going to talk about is we're going to talk about how to compute the standard deviation of a discrete random variable. So, of course, what we want to do is the standard deviation is equal to the square root of the sum of x minus mu squared times the probability of x. So just go ahead and do that. No, I'm not going to have you guys do that. You don't have to worry about that formula. We are going to go ahead and scroll right down to this part. Obtain the mean and standard deviation of a discrete random variable using technology. Because we have technology, why don't we use it? So here's how we're going to do this on our calculators. Okay, this is going to be, we're going to need the graphing calculator for this. Don't forget, you guys can download an emulator very similar to what I have here. Let me just bring that up. There it is. Not that. Not tan. There we go. Okay. So you guys can download this emulator for Chromebooks or for desktops or whatever it may be. We should have the links in Schoology, or you can just let me know if you need those links. So in your calculator, you're going to go to Stat. Where's the Stat button? It is right there. Okay, Stat, and you're going to edit, and you're going to input your data, right? So just like we have our table in our notes here, the X column is going to come first. So 0, 1, 2, and 3. Those are the possible outcomes. And then over here, what we're going to do is we're going to put the probabilities. So the probability of 0 is 0.01. And then we got 0.1 and 0.38 and 0.51. Okay, so now the table in my calculator looks like the table in the book, in my notes. Okay, and now what we're going to do is we're going to go back to Stat. We're going to go over to Calc, and we're going to do a one variable statistics. But the important thing to remember here is one variable statistics, because the only variable is x, but there's a probability of x. And so that's going to be treated like a frequency list. And so we have to show or tell the calculator that there's a frequency list that we have to identify. And so that's going to be L2. So if you guys remember, that means you have to press second 2. So second 2 brings up L2. And now we can go ahead and enter to calculate that. And there's our average of 2.39, which we found by hand. And there's the standard deviation of 0.70562022945. Okay, and yeah, there we go. That's how we can do that using the calculator. Pretty nice, pretty easy, good stuff, okay? So really at this point, that's gonna be it for 6.1. All right, I got, you guys have the PDF of the book on PDF page 10. Let me get rid of that. Get rid of that. Nope, it's not going away. Okay. And on the PDF page 10 is where the practice problems begin. You guys have a couple of practice problems to do. Again, let me know if you have any questions. This should be slightly review of things we've done before. But of course, if you have any questions, just let me know. And yeah, hope you guys are doing well, and I will see you back for 6.2. All right, see ya.